Bismillahirrahmanirrahim. This is our sixth lecture, and today we are going to discuss strain in some detail. In the previous videos, we discussed the basic types of stress and their pertinent considerations. You can refer to those videos for the basic concept. In this lecture, we will focus on why the concept of strain is needed and the main types of strain, normal strain, and the shear strain. If a force is applied to a body, it will obviously change its shape and size. These changes are then referred to as deformations, and they may be either highly visible or practically unnoticeable. For example, a rubber band will undergo a very large deformation when stretched, whereas only slight deformations of structural members occur when a building is occupied by people walking about. Deformation of a body can also occur when the temperature of the body is changed. A typical example is the thermal expansion or contraction of a roof caused by the weather. In a general sense, the deformation of a body will not be uniform throughout its volume, and so the change in geometry of any line segment within the body may vary substantially along its length. Hence, to study deformational changes in a more uniform manner, we'll have to consider line segments that are very short and located in the neighborhood of a point. However, these changes will also depend on the orientation of the line segment at the point. For example, a line segment may elongate if it is oriented in one direction, whereas it may contract if it is oriented in another direction. Now, in this figure, we can see that we are having here three lines. In this undeformed steel rod, this vertical, horizontal, and this diagonal line. After after tensile force is applied on this rod, we can see that the vertical line is elongated, the horizontal line has been shortened, and the inclined line changes its length and rotates. So we can see here that the deformation is happening in all the three directions, as well as it is changing the angles of different fibers of this element. Thus, in order to have a clear understanding of this deformation, we need to introduce another concept that is called strains. Strain is usually defined as the change in length per unit length, but that definition is true for the normal strain. It's something more than just a change in length per unit length. Usually it is measured in experiments, and once the strain is obtained, we can then relate it to the stresses in the material by using the material stress strain law. In this example, or in this figure, we can see that this bolt is joining two glass plates, but this bolt is producing a compression strain in its vicinity in both the plates, and this compression strain is depicted here by these colorful variations, because this image has been obtained under polarized light. Now these strains can be related to the stresses in the material by using the material stress strain law. Mentioned before, normal strain is defined as a change in the length of a line per unit length. This is a very simple definition, and it also gives us this benefit that since it is a dimensionless quantity, we will not have to specify the actual length of any particular line segment. For example, consider the line AB having a length del S in this arbitrary body. If some force is applied to it and it is elongated, then this line AB changes to this curve AB having a length del S dash. The change in length of the line is therefore del S dash minus del S, and thus the average normal strain is depicted using the symbol epsilon, and this is del S dash minus del S over del S. This is the very simple mathematical definition of the normal strain. Previous definition was true for the average strain, but the instantaneous strain or the strain at a particular point is measured using the limit approach concept. For example, as point B is chosen closer and closer to point A, the length of the original line AB becomes shorter and shorter, like del S will approach to 0. Similarly, the change in length will also approach to 0, the new length of the A dash B dash will also approach to 0. Consequently, in the limit, the normal strain at point A and in the direction of n will be limit as B approaches to A along the direction n along which we are taking the strain, and this is the original equation. Thus, this will be the strain at the point A. Now, the deformations not only cause line segments to elongate or contract, but they also cause them to change direction. If we select two line segments that are originally perpendicular to one another, then the changes in angle that occurs between these two line segments is referred to as shear strain. This angle is denoted by gamma and is always measured in radians, which are dimensionless. For example, consider the line segments AB and AC in an originally undeformed body. This AB is aligned along the axis n and AC is aligned along the axis t. After deformation, the ends of both the lines are displaced and the lines themselves become curved such that the angle between them is theta dash. The original angle between them was pi by 2 or 90 degrees, pi by 2 radians or 90 degrees actually. Hence, the shear strain at the point A associated with the n and t axis become this pi by 2 minus the original angle minus this limiting theta or this new angle between the two lines as B approaches A and C approaches A. Since now we have defined the normal and the shear strain, we are at the point where we can use this definition to describe the deformation of the body as is shown in this figure. Let's consider that this body is composed of small elements such as the shown in this figure. This element is rectangular, has undeformed dimensions of del x, del y, and del z, and is located in the neighborhood of a point in the body. If the element's dimensions are very small, then this deformed shape will be of parallel piped. This means that these very small segments will remain approximately straight after the body is deformed. In order to achieve this deformed shape, we will first consider how the normal strains changes the length of the sides of the rectangular element, and then how the shear strain changes the angles of each side. For example, del x elongates. We can see here that del x has elongated. So the change in length will be, or yeah, the change in length will be ex into del x, or the strain into the original length. Thus, its new length will be the original length plus its change in length. Del x plus ex into del x. Similarly, the change in length of the two other sides will be the original length del y plus the change in length, that is the strain into the original length. Same goes with the third side as well. And the approximate angles between these sides are the approximate angle between del y and del z is actually pi by 2 minus gamma by z. Like pi by 2 was the original angle and this gamma by z is the shear strain. So now the angle will be the difference between the original angle and the change that has occurred. Same goes with the other two sides as well. Normal strains cause a change in volume of the element, whereas the shear strains cause a change in its shape. Of course, both of these effects occur simultaneously during the deformation. In summary, the state of strain at a point in a body requires specifying three normal strains, Ex, Ey, Ez, and the three shear strains. gamma x, gamma y, gamma xy, gamma yz, and gamma xz. These strains completely describe the deformation of a rectangular volume element of material located at the point and oriented so that its sides are originally parallel to the x, y, and z axis. Provided these strains are defined at all points in the body, then the deformed shape of the body can be determined. Most engineering design involves application for which only small deformations are allowed. For example, we cannot have excessive deformations like in several order of several millimeters or something in buildings. Usually these deformations are within the range of 1/4 of an inch or something like that. So we'll assume that the deformations that take place within a body are almost infinitesimal. In particular, the normal strains occurring within the material are very small compared to 1. This assumption has wide application in engineering and it is often referred to as small strain analysis. It has practical implications. For example, we can we can safely assume that sine theta is approximately equal to theta, tan theta is approximately equal to theta, and cos theta is approximately equal to 1 because we are running small strain analysis. Now, before moving on to examples, we will first summarize the concepts that have been discussed in this lecture. The benefit of this summary is that we can easily apply these concepts in the examples. The first point is that loads will cause all material bodies to deform, and as a result, points in a body will undergo displacements or changes in position. Normal strain is a measure per unit length of the elongation or contraction of a small line segment in the body, whereas shear strain is a measure of the change in angle that occurs between two small line segments that are originally perpendicular to one another. The state of strain at a point is characterized by 6 strain components: 3 normal strains and 3 shear strains. These components depend upon the original orientation of the line segments and their location in the body. Strain is a geometrical quantity that is measured using experimental techniques. Once obtained, the stress in the body can then be determined from material property relations, as it will be depicted in the next lecture. Last, the most engineering and materials undergo very small deformations. Now, this is our first example. In this cylinder rod shown in the figure is subjected to an increase in temperature along its axis, which creates a normal strain in the rod of this amount. Now notice that they are referring to the strain as EZ. They are not specifying the strain at any particular point. This means that this strain is indicating that it is occurring along every point at within this body. So if we take a segment here, we'll have a strain. We can measure the strain using this equation. If we take a segment here, we can measure the strain using this equation, and the strain in this whole body, or the average strain, will be actually be an integration or summation of all these infinitesimal strains. What we need to determine in this example is the displacement of the end B and the average normal strain in the rod. Before finding the displacement of the end B, we need to first determine what is the change in length of this whole body. So for determining change in length or the new length of this rod, we need to consider this thing that the normal strain is reported at each point along the rod. A differential segment DZ located at position Z as shown in this figure has a deformed length that can be determined. Now DZ dash, or the deformed length, will be equal to the original length plus the change in length, that is the strain into the original length. We have obtained this equation now. The sum of these segments, as I have already mentioned, along the axis yields the deformed length of the rod. Thus we'll take an integration of this differential change in length, and after integrating we have obtained this new length of the rod. The displacement of the end B will be the difference between the new length and the original length of the rod, which comes out as 2.39 millimeter. The second part of the question is simple, that needs to determine that wants us to determine the average strain in the body. The average normal strain in the rod has been determined. We'll assume that the rod or line segment has an original length of 200 millimeter and a change in length of 2.39 millimeter. Hence, simply 2 point change in length divided by original length comes out as the average strain. Remember that average strain indicates the strain occurring along the whole body, whereas the infinitesimal strain or a point strain indicates the strain occurring at a single point of the body. In this example, we are considering a bar or a lever arm ABC. We are considering a rigid arm, so no deformation will occur within this arm, but when a force P is applied on this arm, it will rotate at this location of the support, and we are assuming that it has rotated almost 0.05 radians. We need to determine the normal strain developed in wire BD in this wire due to this rotation. So this slide is a bit tricky. We need to focus here more because some geometry is involved. First of all, consider this thing, that the original angle between this rod ABC and the BD or the wire BD was 90 degrees, right? But now this rod has rotated, so this angle will be actually 90 degrees plus theta. This theta is the angle about which this rod has rotated. Now we need to determine this new angle between this new angle phi between the this rod and this you can say inclined this inclined portion of the rod, inclined line. If we look at this geometry, we can see that 90 plus theta is actually equal to alpha plus phi. How can we determine alpha? That is simple, by using Pythagorean theorem. We can determine this angle tan alpha is equal to 400 by 300 and alpha comes out as 53.13. Now how can we determine phi? As I've already mentioned, we are having this equation 90 degrees plus theta is actually equal to phi plus alpha. Thus, if we solve this equation, it comes out as 90 degree minus alpha plus this theta, and we have obtained this angle phi as 36.92 degrees. Now we can determine this length LAD by using Pythagorean theorem, which comes out as 500 millimeter. Now we are having an angle, a triangle AB dash D. This is not a right angle triangle, so we cannot apply Pythagoras theorem to this triangle, but we are having another law that is called the cosine law, that states that a square is equal to b square plus c square minus 2bc cos theta, and using this cosine law we can then determine the lengths of triangles which are not actually right angle triangle and which cannot be solved using the Pythagoras theorem. Here we can determine this length b dash d, this elongated length, using this Pythagoras theorem, because we are already having the length AD as we have determined here, and we are having the length B dash, which again we have determined, or which was, sorry, the original length of this rod. And we are assuming that this bar ABC is rigid bar, so it will not change. It will not change in its length. Putting all these values in this equation, and we have already obtained the value of phi here, 36.92. Putting all these values in this equation yields us the length of B dash D, or the new length of B dash D as 300.3491 millimeter. Now we can determine the normal strain as the change in length simply by the original length, and this comes out as 0.00116 mm per mm. We have come towards our third example, which is you can say an example in 2D, and it involves both the normal and the shear strain. So this plate has deformed to this new dashed shape due to some loading, and we need to determine the normal strain along the side AB and the shear strain in the plate A relative to the x and y axis. So we basically need to determine this angle and the change in length of line AB. Apparently it seems a very simple task, but let's see how we can proceed with it. Now we need to keep this thing in mind that in this body is experiencing both the normal and the shear strains. So if we want to determine the normal strain or the change in length of this AB dash, it cannot just be determined simply as the difference between the original length to the original vertical length to the change to the vertical or the normal strain. We need to consider this fact that this line AB dash is now an inclined line. So we have to use a different technique to determine its change in length. So 250 millimeter was the length of the original line, and now it has become inclined. So we need to determine that we need to determine this using the Pythagorean theorem. Thus 250 millimeter minus 2 millimeter will be this vertical distance, and 3 millimeter is this horizontal deformation, and combining these using the Pythagoras theorem, we have obtained the new length of AB dash as 248.018 millimeter. Determining average normal strain is then simple, simply the change in length per original length. But grasping this point was critical here, because students can usually make this mistake that they can consider that since we need to determine normal strain, we need to only consider the vertical change in length. But since both types of strains are involved here, we need to take into account this critical fact. The negative sign indicates that the strain causes a contraction of AB. Now we need to determine this angle gamma xy, or the angle between AB and the AB dash. It can simply be determined as the um, this tan inverse perpendicular, which is actually 3 millimeter, and 250 millimeter minus 2 millimeter, which is this vertical change in length or the new vertical length, and then this gamma xy comes out as 0.0121 radians. This is the fourth and the last example of this lecture. It also involves a combination of normal and the shear strains. We are having a plate ABCD which is fixed along this side AB, and it is horizontally supported along the sides AD and BC. If its right side CD is given a uniform horizontal displacement of 2 millimeter, we need to determine the strain or the normal strain along the diagonal AC and the shear strain that is caused at E relative to the x and y axis. Before beginning the formal solution for this example, the critical point of consideration is that there is no vertical deformation occurring in this body, because this side AB is fixed and we are only applying a horizontal deformation here. So the original length of the diagonal AC will be simply determined using the Pythagorean theorem, and then the elongated length AC dash can be determined by using this 2 millimeter, by adding 2 millimeter to the horizontal line segment. So this 1 millimeter will 150 millimeter will become 152 millimeter now, and based on this the length of this diagonal AC dash or the elongated length has been determined as this value. Thus the average normal strain can simply be determined as the change in length per original length. This completes the first part of this problem. Find the shear strain at E relative to the x and y axis. It is first necessary to find the angle after deformation. Thus, we are taking this a half of this theta dash, and tan theta dash by 2 is equal to 76 millimeter, because this is the elongated length, divided by 75 millimeter, the original vertical length, and the theta dash comes out as 1.58 radians. Now applying, we know that the shear strain is actually equal to pi by 2 minus the new angle. So using that equation, the shear strain or the shear strain or the change in angle, you can say, comes out as 0.012 radians. The negative sign indicates that the angle theta dash is greater than 90 degrees. Thank you very much for listening to this lecture. You can ask your questions in the comment section.